I'm going to describe the general behavior that we can get when we start graphing our polynomials just based on a couple things. Mainly, we're going to be looking at what the leading term tells us about the graph. Because the leading term is going to tell us a whole bunch of different things about the activity that our graph does. So first we're talking about end behavior. End behavior is what happens as our x values go towards positive infinity and towards negative infinity. So, on my coordinate system here, as I put in really big numbers for x, that's what end behavior is. As I put in very large positive numbers, I want to know, is my graph gonna shoot up? Is it gonna level out? Is it gonna shoot down? Okay. As I put in very big negative numbers, okay, is it gonna shoot up, level out, or shoot down? So here's the general form of a polynomial function. We've got some leading coefficient a, we've got an x with some power, and then all the x's after that are going to be one less power. So this is n minus 1. So if n was 5, this would be 4, 3, all the way down to 2, 1, and none. So for end behavior, all we have to worry about is what this first term is. Okay, is n odd or is it even? That's the first thing we're going to tell ourselves. So if it's odd, so I'll give you a specific example to work with. Let's say I've got 3x to the 5th. Okay, and then I've got some other trailing numbers here. Okay, I'm even going to make this a minus. Okay, so I've got some function. I'm going to look at just my first term and ask myself, if I put in a very large positive number, okay, so when I approach this side of my graph, what's going to happen to my function here? So think of a very large number, okay, like 1,000. Okay, 1,000 to the 5th power is going to be some astronomical number. Something that's going to be so big that no matter, even though I'm still putting 1,000 in here, this is only 1,000 to the 4th power, and that's pretty much overshadowed by the size of this leading number that I'm going to have. So really, these become negligible as I put in very large numbers. So as I put in a very large positive number, I'm going to get a very large positive number out, and then I'm going to multiply by 3 to get an even larger positive number. So that means the right side of my end behavior, the right-hand behavior, they'll call it, is that it's going up. Now, let's look at what happens when I put a large negative number in. Okay, a large negative number, I'm going to have 5 negatives multiplied together. So that's going to come out to be negative. And then I'm going to multiply it by a positive. So that means I'm going to have positive times a negative, which is negative. So this is my left side behavior. Okay, I don't really know what's going on in between here, but I know at the extremes of my graph, this side's going to be going up and this side's going to be going down. Now, if we change the sign, let's say we change it to a negative 2x to the 5th. Well, that negative is, as we learned from our graph transformations, is going to flip our graph. So that's going to switch what my end behavior is doing. So now the left side will go up and the right side will go down. If we could look at even, okay, let's say I have 4x to the 6th. So if I put in a large positive number, I'm going to get a positive out times a positive and a positive. So the right side's going to go up. If I put a large negative number in here, okay, I'm going to have 6 negatives multiplied together, which is going to turn out to be positive. Okay, any number to an even power is going to be positive. Positive times positive number. I'm also going to be going up as I move to the left. Now if I change the sign here, okay, maybe something like this. Now I'm going to get the positive numbers out, but I'm going to be multiplying by a negative. So I'm going to end up going down as I approach the extremes of my graph. Okay? So end behavior depends on the leading coefficient and the degree of the highest power of x. So the leading coefficient, whether it's positive or negative, that's affecting our end behavior. And if our power is odd or even, that's also affecting our end behavior. So even degree, both ends have the same behavior. So either both up or both down. Odd degree, one's going each way. Now the in-between behavior, okay, so an nth degree polynomial is going to have at most n minus 1 relative mins and maxes. So we'll go back up to these same examples. So here n is 5, so I'm going to have at most 4 relative mins and maxes, which means in between my n's I can have one min, well there's one max, one min, another max, and a last min. 1, 2, 3, 4. That's the most I can have. Now, that doesn't mean I'm always going to have that many. I could have maybe it just does that. But it's possible to have up to 4 of those relative minimum maximums. Okay, and over here I can have a total or a maximum of 5 little bumps. So 1, 2, 3, 4, 5. Okay, or I could have fewer. Okay, maybe I just have that. Another in-between behavior has to do with the roots. So how many times it's going to cross the x-axis in between our extreme values. And whatever the highest power is, that's how many possible real zeros you have. That's the total number of roots that there will be, but not all of them are necessarily real. So let's look at some more examples and try to decide what we know about them. So this one, okay, my end behavior, since I'm negative with an odd power, I know it's going to be up and down. So as I move left, it's going up. As I move right, it's going down. And I can have at most 4 little bumps. Okay. 4 possible min-maxes. And 5 possible real x-intercepts. Okay, remember x-intercepts are the same as zeros or roots. Okay, so these all mean the same thing. Zeros or roots. Here I've got positive coefficient, even power, so my end behavior is going to be up and up. 5 possible min-maxes. And 6 total roots. Up to 6 of them may be real. So, and when we start finding roots, we're going to deal just with the real ones before we break into finding all of them, which would include the imaginary ones. Okay, so now I've got positive with an odd power, so my end behavior is going to be this way. I'm going to have up to 2 min-maxes in here, so maybe it's like that. And it could cross up to 3 times. Maybe it crosses 1, 2, 3. Okay, if this is my x-axis, 3 times. Last one, negative coefficient, even power. So they're both going that way. And I could have up to 3 bumps in there. Okay, the other thing that's going to be in this section here is kind of a transformation review. So all the same rules are going to apply. So what we're going to do is we're going to graph our base function. They're going to tell you what your base function is. You're also going to be able to tell what it is based on what's affecting the parentheses in the problem. So those parentheses are being cubed. That means my base function is just the most simple cube function. If I had like a square root and my parentheses were in there, that means my most basic function would just be y equals the square root of x. So we're going to do the same things that we always did. We're going to plot our base function. So if I put 0 into x cubed, I'm going to get 0 out. If I put in 1, I get 1. If I put in 2, I get 1, 2, 3, 4, 5, 6, 7, 8. Okay, because 2 times 2 times 2 is 8. If I put in negative 1, I get out negative 1. If I put in negative 2, I get out negative 8. So this is my base function. Okay. So if I want to graph this one, my base function is, my starting point is going to move left 2 and down 3. So instead of 0, 0, I'm going to be over 2 and down 3. My base function, I go over 1, up 1. But now I'm going to go over 1. 1 cubed would be 1 times a half, which means I'm going to go down a half. Okay, the negative makes me go down. The half cuts my y movement in half. I was going over 2, up 8. Now I'm going to go over 2, down 4. I was going left 1, down 1, so now I'm going to go left 1, up a half. Left 2, I was going down 8. Now I'm going to go up 4. So this is my transformed function. I didn't connect that very well. Okay, so there's your transformed function. So same things that we went over in the last two chapters, really.